Welcome to this introduction to data management for machine learning and AI. In this lecture, we discuss the question why we would even care about data management in the context of AI systems. Data management for AI systems is not a topic which received much attention by machine learning students or programs. Often, algorithmic topics dealing with fancy algorithms, feature representations, or deep learning neural net architectures just seem to be so much more exciting than dealing with all these boring old data management topics, which have been around for 60 or 70 years. However, I would argue that for every practical AI system which is deployed in a real-world scenario, data management plays a very central role, maybe even one of the most central roles. Thus, AI components and algorithms are just the tip of the iceberg, floating on a huge, often unseen bottom part, which is data management. The goal of this course component is to give you a short glimpse into what data management of AI can entail. Let me start with some statistics. In many surveys among AI and data science professionals, it is frequently mentioned that data-related tasks take most of the effort and time to execute and run a machine learning project, typically amounting to 80%. The precise numbers may vary from project to project, but the rough consensus is what we can see here. First, sources of suitable data need to be identified, and this accounts for about 5% of the effort. Then, data from different sources needs to be aggregated, which is often attributed to another 10%. However, in my personal experience from projects I am involved in, data aggregation typically takes a much larger percentage of these efforts. But of course, this varies between projects. Another large component is data cleaning, which means fixing mistakes and errors, dealing with data with missing data points, fixing outliers, and fixing variances in used schemas. This can easily attribute for another 25% of the effort needed to run a machine learning project. And then comes in data labeling. Data labeling is a very time-intensive task, also easily taking 25% of the project efforts, and typically involves human annotators manually labeling the data. After all these efforts, it often still turns out that data which we have available is insufficient. This starts the data augmentation phase, in which we try to balance data and improve the variety and quantity. And now we already have spent 80% of the project efforts just to deal with data. Also, much of this effort is simply just work, so tedious and time-consuming tasks, but not really fancy from an academic perspective. Yet, this work needs to be done. The actual algorithmic parts of a project are rather small. An average of 3% of the project efforts are spent on developing new machine learning algorithms. This is mostly due to the fact that most people actually don't develop machine learning algorithms themselves, but simply reuse the implementations found in common libraries, which, by the way, is also a good idea. Then, models are trained and tuned, attributing to another 15% of the effort. And finally, the model is being operationalized. From a different perspective, here is a quote from a paper in the Architectural Components of Common Machine Learning Systems, published in 2015 by a group of Google engineers. They argued that the actual machine learning code can be represented just with this tiny little black box you see in the middle of the slides, while most of the software components which need to be developed deal with data collection, data verification, but also a lot with infrastructure tools like configuration, monitoring, process management, and server infrastructure. So, what is our takeaway from all of this? Yes, machine learning algorithms are cool and fun to talk about. Yes, they are very important for the system. However, to build a real-world system, there's also so many more tasks and components to look at, and those actually take the vast majority of the effort, time, and resources. But what is that data I'm talking about, and what do we actually do with it? In order to understand this question better, let's have a look at this very simplified model of general machine learning life cycles. The first step to develop any machine learning system, and by the way, this is also a step a lot of people tend to underestimate or even skip, is studying and understanding the problem you try to solve with your system. This typically doesn't cover any kind of coding or software development, but is a conceptual thinking task where you figure out your requirements, your restrictions, and what kind of system behavior you want to see or not want to see. So this is somewhat comparable to requirements engineering in a regular software project. Then we need to obtain training data to train our machine learning models. Training data here is data which is representative of the data the system will later on work with. In case of supervised machine learning, this training data also needs to be labeled. So for each data entry, we also need to have a label describing what the machine learning model should do with it. For example, if we are training a computer vision system which is supposed to classify images into has a dog in it or has a cat in it, we now would need to have a large collection of dog and cat pictures, each of them labeled with dog and/or cat. Typically, however, it's not as simple as that. We probably also need pictures which do neither contain a cat or a dog, or additionally need to make sure that our dogs and cats are covered from different angles and different light conditions and cover enough dog and cat breeds. Long story short, in order to make a good system, we need good training data. If our training data is bad, the trained system will also be bad, no matter which kind of fancy algorithm was used. After we trained our machine learning model, we need to check if the model performs well and, well, thus if we did our job well. For this, we use testing or validation data. This is also labeled data, but has stricter requirements with respect to quality than training data has. Thus, we really need to be sure that the labels of testing data are correct, because otherwise all tests and evaluations we do with that data will also be unreliable, and then we do wrong decisions. If this evaluation of the model results in the model being insufficient, we go back to square one. This could either mean that we misunderstood the problem completely and that a different approach is needed. Or it could also mean that the training data we use was just insufficient for the task and that providing better or more diverse data will already fix the issue we encountered. Or it could mean that tuning the machine learning algorithms or choosing a completely different algorithm will result in the desired distant performance. If the model was evaluated positively, well, good for us. Then we can deploy the model. This does typically not mean that we are done. Missing from this diagram is that as soon as real people start using a machine learning model in real application, it often turns out that our training data and testing data did not cover all the weird edge cases or all the arcane things real people would try to do with real systems. Therefore, often, even after deployment, continuous tuning and improvement of both algorithm and the testing and training data is needed. So, to summarize again, what kind of data do we need? We need training data to train and fit our model. Often during the training process, we also need to run many continuous evaluations to guide the training process itself. For this, we typically use validation data, which is a kind of testing data. In fact, many people use the term validation data interchangeably with testing data, but there are slight semantic differences here. After we believe that the model is stable, only then we use the real testing data to decide if the model is ready for deployment. Just to re-emphasize the point of testing data. The role of testing data is to decide if the model is actually behaving as it should. Therefore, engineering this testing data is a very important and central task, as it needs to cover all relevant edge cases which a system needs to handle. Many real-world scandals where AI systems turned out to be racist or sexist or otherwise misbehaved can be traced back to training and testing data not being complete and balanced enough. You probably heard a lot of these stories before, or will hear them in the future. For example, automated job application systems rejecting female applicants because the dataset which was used in order to train them mostly covered male applicants. Image classification systems misclassifying people of color as gorillas because the training dataset mostly contained white males. Or people credits application being unrightfully rejected by their bank because the training data did not cover all relevant demographic groups. Look out for specialized courses on these topics, typically running under the names of Responsible AI, Reliable AI, or Ethics of AI, to learn more about these problems and issues. But then keep in mind that in most cases, the underlying cause of these problems was insufficient or even thoughtless data collection. Okay, let's have a quick look at labels again. Labeled data means that the data points in the datasets are annotated with the desired outcome or the desired decision the system should take. So, for a classification task, we would have class labels. In case of unsupervised training, we might get away with having unlabeled data. However, for testing and evaluating the system, we will always require expensive, high-quality labeled data. Let us also summarize what makes good data. First off, data should be relevant, which means it should fit and be relevant for the task you want to address with your system. Well, this sounds very, very, very obvious. But as I will discuss later, training data is often shared and reused between different projects, and is thus not always a good and relevant fit for the task. Also, data needs to be representative of the data the system is going to work with after deployment. Also, relevant edge cases and classes need to be sufficiently covered. Another requirement, which is also quite obvious, is that data should be uniform, which means that all data in the dataset should be sharing a similar structure or schema. Sounds obvious, but this is actually not that easy to achieve when data is being aggregated from different data sources and collected in one place. Furthermore, data needs to be comprehensive, or to rephrase this, the data needs to be big enough. Many modern machine learning algorithms are very, very, very data hungry, and especially deep learning models require a humongous amount of training data in order to tune their thousands or sometimes even millions of parameters. For example, GPT-3, a state-of-the-art language model, is trained on about 45 terabytes of text data aggregated from several sources. Using less data than that would actually negatively impact and degrade its performance. And finally, we need, of course, to make sure that we have the labels available where labels are needed. Let me close this lecture with this common saying. If you put garbage into your system, garbage will come out, or simply garbage in, garbage out. We need to be aware that data management is a central part of the machine learning and AI workflow, and that it takes a lot of time and effort, and that data we choose has a very strong impact on the potential effectiveness of a system. We need to find good training data and testing data. Often, this also means that data needs to be labeled to make it useful. Obtaining such data at high quality is very hard and can be extremely expensive and time-consuming. Let's keep this in mind for the future. And with this, I will thank you for your attention today and hope to see you another time.